All right. So for an application now. The position function gives the height in feet of an object that has fallen for t seconds from a height of 500 feet in this case, because we have that 500 in the function. So there it is, s of t. And the velocity at time t equals a is given by, the limit as t approaches a, of s of a minus s of t divided by a minus t. So we'll put that up there. So a can of paint falls from a height of 500 feet. So the picture here doesn't really do it justice. It just looks like we have that on a bit of scaffolding. How fast will the can be falling after 2 seconds? So again, not to scale, obviously. So the paint can is going to fall. How fast was it falling after 2 seconds? So we know that this thing is going to be 500 feet. And so we're given the position function right here. The time is t equals 2, we know. So we can evaluate s of 2. That would give us 436. So what are we doing here? Well, since the velocity is at time t equals a is going to be 2. So if we replace a with 2, this is what we end up with. So we just want to replace that now. So the limit as t approaches 2 of 436 minus that function divided by 2 minus t. And if we simplify, we can factor this thing. And so it turns out to be 16 times t squared minus 4 over 2 minus t. And we can do a little bit better. We could factor that, factor out a negative, and then cancel it. And so we end up here with negative 64. And that's feet per second. All right, so when's it going to hit the ground? Well, we pause right there. So we want to know how far along is the paint can. How many seconds has it taken for it to hit the ground? And that's not too bad of a question. The position, or the height, is just going to be 0. So, simple algebra. And we end up here with 5 square roots of 5 over 2, and that's good enough. Okay, so we want to look at what an actual limit is and what it represents if we're letting x approach c. So let's say we have some function f. So right now it looks like the height of f at c is L. We can put lines here. It looks pretty accurate so far. But we want to show that if we're getting closer to c, then we're actually getting closer to L. That means its limit. So let's say we have a very small number, delta. Then we're going to add delta to c, but we're also going to subtract it from c. Now we're going to do the same thing to L. We're going to add a really small number that we call epsilon to it, and we're going to subtract it. So what we have here is this little box that we can form around C and L, or the point CL, we should say. So our claim is that that delta and that epsilon that we added to C and L respectively have some relationship. It might be delta equals epsilon over 2. It might be delta equals 6 epsilon. We don't know what it is, but there is some relationship there. And so what that means is if we make delta smaller, epsilon is going to have to become smaller as well. So let's let delta become smaller. Now look what's going to happen here. C minus delta, C plus delta, they're going to get closer together. They're going to get closer to C. And look what happens to the box when that happens. Epsilon also got smaller. The box is closing in on that orange point there. If we do it again, notice that orange dot is still inside of the box. And if we were to zoom in on the function and just keep doing this repeatedly and repeatedly, the dot's always going to be inside of the box. It's never going to come outside. And what that means is we found the limit L. As x is approaching c, f is approaching L. And as long as it doesn't come outside of that box, we're good. We found it. So if we can make the walls close in on c, that means the ceiling and the floor are going to close in on L. And that means that we have the limit.